Hi class, welcome to chapter 4. Chapter 4, we are going to study a little bit more about first and second derivative again. We briefly studied in chapter 2 about the shape and then what it means a little bit, and we are going to deeper understanding of first and second derivative. So let's look at the appetizer. When you look at the appetizer, here says find the vertex of given polynomial function. As you see, x squared minus 2x minus 3. So how do we find this vertex? When we find the vertex with pre-calculus way, we plug into formula negative b over 2a, which is negative 2 over 2 times 1. So I get 1 as my x value. Then what's going to be your y value? By plugging 1 here, I get negative 4. So I get my vertex as 1, negative 4. This time, let's look at what we can do about in calculus, because I know that vertex means my graph looks here, and then vertex happens at when my derivative function, which the slope is equal to 0. Which means, what does that mean? That means, the slope is 0. So I'm going to take a derivative and then set equal to 0. So let's take a derivative that will be 2x minus 2, which has to be equal to 0. So if you solve for x, you are going to get x as 1, which is the same as this. And then by plugging 1, you will get negative 4 as well. Yeah. So I want you to see the differences, but they are basically the same. And then finding the vertex, you can use formula, or you can use the slope here. So by using that, we can use 1, negative 4, and then graph carefully. Also, do you see that it factors as a 3, 1, x minus 3, x plus 1? So it passed through 1, negative 1, and 3. So that's how we can graph. But let's briefly also study. I know that you understand this part, so we can graph it. But from here, what we need to learn is what's gonna look like in your derivative graph when you have a 2x is minus 2, which means when x is equal to 1, what happened? What happened? So do you know how to graph 2x minus 2, which is our derivative function, which starts from negative 2, slope 2. I'm going to graph it. So I want you to look at my red color, which is our derivative function, 2x minus 2. I like to recall one more time, what does this mean from here? From 0, which my slope was 0, below the x-axis means what, class? My function of original function decreasing. If my derivative function is above the x-axis, that means my original function is increasing. Therefore, analyze it. This means decreasing, this means increasing. Decreasing, increasing. That means at that moment, what does that have to be? Has to be local minimum. Has to be local minimum. So careful about that. Then today, we are going to study about what critical number is. What critical number is. The critical number is just to take a derivative that makes equal to 0, which is like this one, right? Or it does not exist. What does that mean? It does not exist. That means a vertical slope, right? Or undefined. So remember, critical number has 2 meanings when your derivative is 0 or do not exist. Then each of them will have a different meaning. So wait for me for next one. So now let's do one more time with our appetizer. I want to actually graph this one using pre-cal way. So in pre-calculus class, how did we graph? By factor, and it will vector out by this. Do you guys see that? I did it whole thing at once. I'm sure you can do it too. So if I'm using my pre-cal, that's how we graph. That was it. Then now, what can we do in calculus? We can actually find these values better. Before, with quadratic, it's easy to find your vertex, but if it's x cubed, actually we cannot call the vertex but maximum minimum point. These are actually related to your derivative. So let's take a derivative, which will be 3x squared minus 4. So now, what does that mean? I want to see that when I look at the derivative, and if I want to find these two values, they are make my derivative slope as a 0. My slope is equal to 0 at this. Then what is the x value at the time? What is the c value at the time? So all I need to do is to solve. 3x squared is equal to 4. So x is equal to 2 over root 3 plus minus. So if you punch into calculator quickly, then that will make 1.15. It's about 1.155. So that means this value here, that's 1.155, comma, the other side will be, since we have a plus minus, negative 1.5155. And by plugging this number, you will be able to find y value. So let me plug in y value quickly in here. So I'm going to plug in 2 over root 3 into my original function so that I can find actual value of the maximum and local minimum. You can try together with me, please. Okay, so I got negative 3.079. 8. Then this will be positive 3.08. I can see that it's going to be odd function, right? So compared to pre-cal, we just found x-intercept, and for us, we couldn't find those two peaks because there's no way that we can find maximum minimum value. Since now you guys know the calculus, we can find those values. So now let's answer one by one. What are the critical points? Critical point, don't forget, that means equal to 0 or not exist. So this time, what makes equal to 0? That will be plus minus 2 square root 3. Those two are the critical points. Then local maximum. So what is going to be local maximum? They are talking about this one. They're talking about this one. How do I know that that is local maximum? Well, by the graph, but also let's look at graph way. If I graph this one, 3x squared minus 4, that will be, graph looks like this way. Look carefully. Then what does this mean here? We talked about earlier, if it goes red color, my first derivative is below the x-axis and above the x-axis, it change means decreasing and increasing, decreasing and increasing, so it becomes a local maximum. So now look at this time, it's going to be above the x-axis and then below the x-axis. So above the x-axis means increasing and decreasing, so this point is representing local maximum, which is negative 1.155. So you cannot just assume that is a local maximum minimum when you look at this. Why? We cannot tell that is a maximum minimum. So how are you going to tell? You have to check with the first derivative graph. It shows that my graph is going to be, original function is going to be increasing, decreasing. Therefore, it has to be local maximum value. So x is negative. Actual value is negative 2 over square root of 3, which is about negative 1.15. Okay. So same reason. If you understand this part, actually it will be easier for later. And class, please listen all the explanations because it will be very helpful for you. And 4.3. So local minimum. Where is local minimum? So look at this part of the graph. Do you see that at 0? My first derivative is decreasing, increasing, decreasing, increasing. What does that mean? My original function will be local minimum. Where? Plus 2 root 3, which is positive 1.155. Then, what is the inflection point? What is the inflection point? Do you guys remember? That is come from second derivative. First derivative shows that increasing or decreasing. Second derivative shows that concavity and inflection point. So let's take derivative one more time. If I take a derivative one more time, that's going to be 6x equal to 0, right? 6x equal to 0. That means x is 0. What does that mean? My inflection point is at 0. If you plug in 0, it becomes a 0, 0. So inflection point is 0, 0. So look at this blue color. Does it make sense? By taking first derivative graph function gave me where local maximum minimum is. Second derivative function gives me where the inflection point is, which is 0, 0. If you look at, do you see that my concavity changes? So this is it. There's now in-class activities for you. I want to pause it and try and compare with me. In class, let's look at in-class activities. Of course, it's not really hard question, right? Since you did in algebra, but let's just try to see the point of what we try to learn in here so that we can apply a little bit harder one later. So I rewrote it and then it didn't factor, and I see why it didn't factor. So I used the pre-cal way and then plug in negative b over 2a. I got 2 plugged in into g, I got negative 1. So I found my vertex will be 2 and negative 1. So I graph it because it's going to be negative, it's going to be open down graph. It's going to be open down graph. So I graph this one, and then as you see why it doesn't factor. There's no x-intercept, right? Factor means you will have x-intercept. It doesn't factor, that means no x-intercept. Now let's move on to calculus way. What I did, I took a first derivative and then I took a second derivative. So let's say that first derivative tells me critical point. So critical point is going to be at 2, which makes it 0. And now you have to be careful from here. How can you say that this is a local maximum or minimum? Everybody remember how we graph this? Negative 2x plus 4. If we graph it, it's going to be y-intercept at 4, and then slope is a negative 2. So my graph looks this way, and then look at here. This is exactly when your slope is 0. Then, by looking at it, red color, what does this mean? My original function is increasing and decreasing. Increasing, decreasing. It has to be local maximum. You have to show that y has to be local maximum. In this case, my first derivative graph show this way. In order to be local maximum, it has to be increase and decrease graph. And you see this shape. And then local minimum will be this shape, which you don't see it in here, therefore we don't have a local minimum. And then how do we find inflection point, which means second derivative has to be equal to 0. So I took a second derivative, which is negative 2. Is that equal to 0? No. So we do not have a inflection point, which means when you look at concavity do not change. So it all makes sense to you, right? Okay, so let's talk about our main dish. I kind of want to squeeze here because this one you have seen before, and then I'm gonna mention, and then we are going to see how we can graph the original graph by knowing first and second derivative properties. So let's look at our function shape. When we have function looks this way, and also we can have this way or this way. This more looks like x squared, other one looks like concave down, and then right side looks like more as function of the polynomials. Then how will look like our first derivative? What will be our first derivative? We talked about where will be 0. Easiest point is finding where slope is 0. There is going to be 0. And then what happened to my slope? My slope is here negative as a decreasing, so below. And then right side, my slope is positive, so it's going to be above the x-axis. I know I've been mentioning a lot, but I want you to remember it's going to keep building up and for the next section. So if I have a graph like y is equal to x, it's an increasing graph, but I have a 1, 0 here. What does that mean? This show me that I must have local minimum or maximum. Minimum. Keep thinking. It's a decreasing, increasing, decreasing, increasing. Then I want you to think about this one here. How do we graph on first derivative? There's a 0. So here's going to be 0. And my slope is going to be positive and then becomes a negative. So my slope positive above the x-axis and negative below the x-axis. That's how your first derivative look like. Then let's look at next one. What will be second derivative look like? Oh, we have to mention that now. This means your original function is increasing, decreasing. Therefore, what is that point? Local maximum. It has to be local maximum if it crosses x-axis. It has to be local minimum. It crosses x-axis. Depending on how the shape is this direction or that direction will determine maximum or minimum. Now, second derivative indicates the concavity and inflection point. So, if I take a derivative of this one, everybody see that it's a positive derivative everywhere. So, above the x-axis. Also, everywhere positive, my graph is going to be above. If you look at this one, everything will be negative, so it's going to be below. So that's my first derivative and second derivative analyzing here. So if my second derivative is all above the x-axis, that means concave up. If it's below, then concave down. Okay, now I want you to pause and then think about the next two graphs. Let's compare to now x cubed and negative x cubed derivative graph. So did you see that concavity changes? So at that moment, my slope is going to be 0. But as you see, this side is slope positive. This is also slope positive. So both will be above the x-axis. Kind of feeling weird, but that's how it looks. And next one, also same reason. If you see when concavity changes, it's going to have a slope 0. And also just think about it as a limit, right? And here slope negative, and then here also slope negative. So both sides of your first derivative function has to be below the x-axis, as you see, negative and negative, right? Then now, if we take the derivative of this one more time, which you will see, these are the same thing, right? The original to first derivative to second derivative. So if I take a derivative, that means, where's the 0? That's a 0 here. Where's the 0? That is 0. Decreasing, increasing, decreasing, increasing, increasing, decreasing. So now, what did we say about second derivative? Second derivative tell us about concavity. And the first derivative is increasing and decreasing. So look at here. If your second derivative is below the x-axis, that means concave up or down? Concave down. So do you see that? Concave down. And then that's above the x-axis, concave up. And what is this? Therefore, this becomes inflection. Inflection point. Same reason. Now when you look at here, there's a concave up, concave down. When concavity changes, it will make an inflection point. So therefore, there is an inflection point. Okay. Then let's study next one. So main dish says discuss those 4 different first derivative functions on x-axis. Did I say it correct? First derivative function. So y is equal to 2x. But my first derivative is 2x. That is my first derivative. Then what can I say about this moment? Is this local maximum or local minimum? That's how I try to ask. So that's the first derivative graph. Then that's gonna be local minimum. Young, I get confused. Then think about this way. What does that mean? First derivative as a negative means my graph is decreasing, and the next one is going to be increasing, right? So what is this point? It has to be local minimum of original function. Think about next one again. Negative 2x function looks like this way. So my first derivative is negative 2x. Then what can you say about my original function at 0? Is this going to be local maximum or local minimum of my original function? Which will be, here it says increasing on my original and then decreasing on my original. So this point means local maximum. That represents local maximum. So keep relating, keep relating. And now I want you to try next two. I want you to draw that and then compare what this means. So class, this is my first derivative function. Then what does this 0 mean in this case? Before, if your sign changes minus to plus, then it becomes local minimum. Plus to minus becomes local maximum. Then how about plus to plus? I still have a 0, but my first derivative sign is a plus and plus. What does that mean? That means increasing and increasing, right? So what does this 0 means? It's going to be inflection point. Did you understand while you were doing it? If not, you get it now, right? So think about this one again. Now my first derivative says decrease and decrease, but also become a 0. So decrease and become 0. What does that mean? That is going to be function look like this one, which is negative x cubed. So I want to take a derivative of this one. Do you get that negative 3x squared? Yeah. And what does this 0 mean? When the sign doesn't change, that becomes inflection point. When sign changes minus to positive and positive to negative, those are the local maximum or local minimum. If all those is equal to 0, if sign doesn't change, then you can say as inflection point. Now, are they all equal to 0 on your first derivative? Yes, those are 0, 0, 0, 0. But depending on if it's positive, positive, then it becomes inflection point, which you can also check as a second derivative. So keep studying. So the next main dish 3. What does this mean? Now we have information about first derivative and then second derivative. So using that, we are going to guess what will be our original function. So here says, it's a little bit hard to see on mine, right? So staring at your paper, and my first derivative is everywhere negative. Then my second derivative is positive. Listen mine carefully. So here you have to see first derivative is negative is this case. Do you guys see? This is a negative case. And then another one is this is my first derivative is negative case. So I have those two cases. Then next one says my second derivative is positive. I have so many pens going on, right? So both are my first derivative negative satisfies. And then second derivative is a positive. Which one is it? This one or the other one? This is it. So it satisfies in this interval. First derivative is a negative. Second derivative is a positive. Then your graph shape has to be this way. So I'm going to connect. Then next one, first derivative is negative, second derivative negative. So both has to be negative. So this is a negative. If you don't get it, my first derivative is a negative. This one is a positive, right? Above the x-axis. So negative. And then second derivative is negative, which is will be this case. Then my function will look like this way. So what am I doing is I break into 4 cases. 1, 2, 3, 4. And look at negative, positive, you get that shape. Positive, positive, you get this shape. If you have a positive, negative, you get the concave down shape. And then negative, negative gets concave down with right side. So you have a 1, 2, 3, 4 choices. So that's how I'm doing. So now I have a negative and negative. So negative, negative, my function has to look concave down, which is this way. Now next condition says first derivative negative, second derivative positive. First derivative is negative, second derivative positive. So that will be this case again. So you are going to have this shape number 1, and then last one negative and negative, which we have seen it, negative, negative. So you will have graph this one. And now do you see those conditions? Let me read carefully. Yeah. Second derivative here says the second derivatives are all 0. What does the second derivative mean? That means inflection point. So inflection points are here. Do you see this is inflection point, this is inflection point, this is inflection point. What does inflection point mean? Concavity changes. So that's how I can graph. Now, it's your turn. Same idea. Compare 1, 2, 3, 4 cases. You are going to have this part and the other part and look at the sign carefully and guess and compare with me. Okay, it's not easy when you do it by yourself, right? So that's what I got. And then when I look at it, right side was pretty easy. Positive, positive. So when I look at positive, positive, it has to be this shape. So it looks like parabola and right side. And then now you have to be left side a little bit careful. First derivative is equal to 2. That means your slope is 2 everywhere. That has to be linear equation, right? Only linear equation. Also, if you think about second derivative is 0, that's only linear equation case. So I put my linear equation with the slope 2 connect with other side at 2. I made it my slope like a 2 so that it connects each other. So my graph, if I kind of look like linear equation and then connect with my quadratic function, where you see that they kind of changing some of the concavity. That's why y prime is second prime is equal to 0. And then at that time, this slope and this slope, the limit of the rate of change, both are going to 2. Okay. So okay, now meet me at the dessert. Okay, so let's look at our dessert. Now we are going to use the derivative to find the critical points and inflection points. So earlier we saw the four cases of your first derivative, this case, and then this case, right? And these are first derivative. And remember, what is this? Local maximum, increasing, decreasing, local minimum. What is this one? It's going to be increasing, so it has to be inflection point. So increasing, inflection, and then decreasing, like that, of the original function. So it's inflection point when first derivative shows this way. So now when we look at this function, let's find given critical points. Take a derivative. Do you guys see that it's going to be, I see product rule and chain rule inside. So do you remember product rule? Take a derivative, which will be 2, and then leave it, don't touch anything, plus leave it, and then now take a derivative, and then chain rule here. So after that, careful, we need to combine the like terms. So I'm gonna pull all the factors out. 2e to the negative 2x, that will be 1 plus negative 2 actually. Okay, so that's my first derivative. Then let's find the critical points. What does critical points? Either it makes it 0 or undefined. So from here, I'm gonna say equal to 0. Now think about 2. Can 2 be 0? Never. Now here, e to the negative 2x, can it be 0? Never. Why? Because if you graph it, your graph is going to look like this way, never going to touch x-axis. So this one never 0. Never. We cannot find any x makes it 0. The only thing that can make it 0 comes from this part. So solve for x here, then 1 minus 2x, 1 is equal to 2x, x is equal to 1 over 2. So I found critical point. I have only one, which is 1 over 2, when x is 1 over 2. Okay, then what is this point? Is this critical point represents local maximum, minimum, or inflection point? How do I know that? So is this one, or this one? How do I know? Well, we have to look at our first derivative, as I mentioned. This one cannot be 0, this one cannot be 0. So I'm going to graph this one. 1 minus 2x. 1 minus 2x. When I graph it. Now, do you guys see that what is this point? That is 1 over 2, which you already found, right? Whatever makes it 0. Then, look at my graph. Increasing, decreasing. Do you see that's my first derivative? Here says, oh, my original function is increasing. And then after that, after 1 over 2, it's going to be decreasing. Then, what does that 1 over 2 of critical point mean? That is going to be local maximum. Young, I'm confused. Well, graph 1 minus 2x, which is I get this. Do you see that if graph shape like this makes a local maximum? That's why how I got local maximum as 1 over 2. And then if you will have x value at 1 over 2, it's local maximum. Do we have a local minimum? No, because I only have one critical point, which is 1 over 2. So we don't have a local minimum. Do we have an inflection point? We have to take a derivative again, right? Inflection point is going to be second derivative. So let's look at this one and let's take a derivative very carefully. I didn't think that I need more room. So if I take a derivative one more time, do you see that I have to use another product rule, chain rule in here? So taking second derivative, that will be take a derivative 2 times e to the negative 2x negative 2, and then leave it, 1 minus 2x, plus, now leave it, don't touch, and then take a derivative, negative 2. So staring very carefully again, what are the common factors? Do you see common factors? I see this one, and then negative 2, negative 2. So we can all pull out as a common factor. which will be negative 4 e to the negative 2x. Inside I have a 1 minus 2x plus 1, right? Since I pull everything out, I should have a plus 1. Negative 4 e to the negative 2x and 2 minus 2x. Okay. So from here, do you see x has to be what? 1. When x is 1, that will be equal to 0, and they cannot be 0, they cannot be 0. So it's going to be when x is 1, that will be 0. What does that mean? There will be inflection point. So not always inflection point will be shown on first derivative, but it always is shown on second derivative. So I got 1. Now I'm going to back substitute and then plug it back to my original function. If I plug in 1, my inflection point is going to be 2 times e to the, okay, I get 2 times e to the negative 2. And then if I plug in 1 over 2, that's going to be e to the negative 1. Do you agree? I substitute 1 over 2 cancel out, 1 over 2 cancel out. So that's what I get. Then why do we have that? Can we graph this? We're using these informations. Yeah, that's what we try to do. So now we are going to graph here. First, I know that local maximum is going to be 1 over 2 and e to the negative 1 is about 0.37 something. So the number I will put it here. That's still maximum. So I will make this one 0.5. And then this is 1 over 2. And you have to understand this one for 4.2. So please listen. So here is going to be 1 over 2 comma e to the negative 1, which is 1 over e as my local maximum. Then inflection point is going to be 1 comma. You can punch into this one to the calculator. 2 times e to the negative 2. I get 0.27. Now you have an inflection point about here, 1 comma 0.27. And other information you know is here. What does it here say? Concave up or down? Oh, not concave. What does it here say? Here says my graph is increasing and decreasing, right? So over 1 over 2, it has to be increasing and decreasing. Concavity changes, so it's concave down and then it's going to be concave up and then going down this way. Youngha, how do I know that? How do you know that your concavity? Now look at here. It has to be positive. This is a positive, so put negative here. That will be, we need to graph it actually. Negative 2 minus 2x, which is 2x minus 2. 2x minus 2, if that's the graph I'm supposed to do. Then from 1, here says concave down at 1, concave down, and then after 1, concave up. A lot of information for dessert 1, right? So now this is the shape of the graph, and this is the function that a lot of chemistry and biology uses for drug dosage or caffeine. Like when you, after you're taking a medicine or you're taking the drinking coffee, what happens is within 1 hour it shoots up and then after that it drops down, right? So that's why I spent some time to study a little bit more. So review one more time and you will see one more time at 4.2. So make it yours. You will keep look at same question, similar question. I will do one more. Okay class, let's look at one more example. Keep looking. It's gonna build to 4.2, 4.3. So keep doing it with me. This time I wanna find the critical point. That means let's take a derivative and see that one makes it 0 or undefined. So it's going to be 1 minus 1 over x. Okay, so now I'm going to make it 0. Then 1 over 1 is equal to 1 over x, right? So what is the x? X is equal to 1. So 1 is equal to 1 is going to be 0. Also, can it be x? Can x be 0? Yes or no? Tricky, right? Because this one is not going to be in the domain. So critical point will be only x is 1. Then we have to show that is this going to be local maximum or minimum? Uh-oh, how do I know? Do you guys remember how to graph this? Or do you guys remember 1 over x graph? And then do you know 1 over negative x graph? And then we do plus 1. So let's look at the shape of the graph. That is going to be 1 over x is this shape, and negative will be this shape, and then move up 1. So I'm going to have move up 1 and this way. Everybody agree with me? So from here, when x is a positive, so I'm looking at this part, and this is my first derivative graph. Where is the 0? What is this value? They said that value is 1. Then look at my graph. Earlier we said that if it's like this and this, here's a 0, here's a 0. What does this mean? Local maximum or minimum? This is local minimum. How do I know? Decreasing, increasing. And then this one, local maximum, increasing, decreasing. So when I look at this one, can you say that it's decreasing, increasing in your original function? Decreasing, increasing in your original function. So it has to be local minimum. You have to show, you cannot just say this one is a minimum. So you have to show me by the graph, and if it's a negative to positive, then it has to be this shape, that local minimum at 1. If I plug in 1, what do I get? 1 minus natural log 1 is 0, so 1 comma 1. So I get local minimum at 1 comma 1. Then let's look at inflection point. Let's take second derivative. That will be negative. So if I rewrite it this one as a power function, do you see that 1 minus x to the negative 1? If I take a derivative, 1 goes away. Negative 1 to the x to the negative 2. So I get 1 over x squared. That's my second derivative. Then what it makes a 0? Is there anything makes a 0? No, there's nothing makes a 0. Then do I have an inflection point? No, I do not have an inflection point because the x has to be greater than 0. Then another information we know is it's going to be there's a decreasing and increasing, and that's going to be local minimum. And then starting value, when we plug in 0, it's going to be 0, right? When we plug in 0, undefined. And then when we plug in 1, that's going to be passed through 1. So what I can see is here's 1 decreasing and increasing, something like that. So that's how I guess my graph. Class, just for fun, I plug into x minus natural log of x, and then that's the graph you see, and then that's my guess. Not bad, right? So there's an one more question of yours, and then I want you to think about it. And then compare the answer with me. Okay, let's look at our in-class activities. So I took the first derivative, and then that's the first derivative. This is the second derivative. So from the first derivative, I found my critical point will be at 1. E to the negative t cannot be 0. That's why we cannot find 0 in here. Graph shapes, this one never touches. So this one never gonna be 0, that only 1 minus t can be 0. So I can see that this is a critical point. Then what does a critical point mean? It can be local maximum, local minimum, or inflection points, right? There are 4 cases. So when I check this one, graph y is equal to 1 minus t, which is decreasing graph, and then the x-intercept, which is going to be 1. So what does that mean? It's going to be, first derivative graph is going to be negative and positive, because this is always a positive. That's why it doesn't matter. And then this function that's a positive, negative of the first derivative means positive, negative. It has to be local maximum at 1. So I plug in 1, and I get 1 comma 1 over e as my y value, and then that means I'm not going to have a local minimum value because I only have a 1 critical point, which is a maximum. And then second derivative, if you take the derivative this one more time, I use the product rule and chain rule. So look at my work and do it one more time. Then same reason, this one never gonna be 0, that this is only 0. So t has to be equal to 2, which is going to be inflection point. So by plugging original, it will be 2 over e squared is going to be inflection point. So I have an information that's a local max inflection point, and then here is going to be increasing, decreasing. So increasing and maximum decreasing, and then inflection point. So it's going to be concave down and concave up. Or make it a little bit better, concave up. So this is going to be shape of my function. Okay, so I hope you understand. We will see this one again and again. So keep doing with me, and then I will see you next class. Good job.